Okay, so remember what we're doing? We're talking about uniform convergence, right? So like what the good things about uniform convergence as opposed to pointwise convergence, right? So pointwise convergence, had some qualities that weren't so good. Uniform convergence, like what we showed last time was that so basically we're looking at good properties of uniform convergence. Okay. And what we showed last time was that if you have uniform convergence and you have that these guys are continuous, then f is going to be continuous, right? So uniform convergence of continuous functions guarantees that the thing that they converge to is continuous. Previously, we had seen that that doesn't hold if you just have pointwise convergence, right? And what we're going to see today are two things, maybe. One is that if these guys are integrable, if the things that are converging the things that are uniformly converging are integrable, then the thing that they converge to is integrable. And then we're going to see something that is not quite the same thing in terms of differentiable, because the statement with differentiable here is actually false. But if you impose a bit more conditions on it, then you can get something that is true. Okay. So first we're going to be doing this one. Okay. But before that, we need sort of a crash course or crash review of what Riemann integrable means. Okay. So so this is the one that you saw in. This is the thing that you may have seen in calculus, but it's probably we're going to do it a bit, slightly more rigorously now. Okay. Okay. So let's see. Let's do it over here. Okay. So here's the definition. So you have a function, a real valued function on a closed and bounded interval, and it's bounded. Okay. So when we're talking about Riemann integral functions, we're only talking about bounded functions. Okay. So then we introduce a couple of definitions. The first thing is called a partition of the interval. Okay. And a partition is just a very simple idea. It's that you take your interval and then you divide it into pieces. Okay. So a set of points P being x0, x1, x2 through xn. So these guys are all in AB, is called a partition of AB if they're increasing, they're strictly increasing, and the first one is A and the last one is B. Okay, so it's a long thing, but all it means is that you've got a bunch of points going from A to B. Right? You got a bunch of points x0, x1 through xn going from A to B. Okay. So let some notation. Let m sub I be the supremum of f on xi minus 1, comma xi. Okay, so your function, right, you have some function on this interval, and for the ith interval, m sub I is the supremum on the ith interval. Okay, right. So the highest, biggest value on the ith interval, right? And little m sub I is going to be the infimum on that interval. Okay. Delta xi is going to denote the width of that interval, right? And then we define this thing UPF, which is called the upper sum of f on P. Okay, and UPF, all that means is that you're going to take the maximum value on each interval and then multiply it by the width of the base. Right? So you take the maximum value, you multiply by the width of the base, and you get the area of this dominating rectangle here. Right? And then you add all those things together, and that's called the upper sum. Okay. And then you do the same thing below, you call that the lower sum. Okay. So this is going to be summation capital M sub I delta xi, and lower sum df is going to denote summation of the lower values times the widths. Okay, I'm sure you've seen this sort of thing before. Or if you haven't, you've probably seen something very similar to it. Okay. Everybody following along? It's just some ideas that we're just sort of like codifying some things that you've seen before, I think. Okay, so let me ask you this: if I change the partition, suppose I throw in an extra dot here. Okay, suppose I throw in an extra dot here. What happens to the upper sum? Suppose I make the partition a little bit finer by throwing in a dot. What happens to the upper sum? What's the relation between the new upper sum? Is this new upper sum bigger or smaller than the old one? Anybody? Do you want to talk to each other? Talk to each other for 1 minute? Talk to each other for 10 seconds?
Context of that particular one. I think it should be either the same or smaller. It's like
Okay.
at best it's a flat line.
Right. So
Or it's lower.
here's your original ith interval, right? You have the maximum here, right? Now we break it into smaller pieces, and we take the maximum over those smaller pieces, right? What happens to the maximum? Well, the maximum on this side is going to get lower, right? The maximum on this side stays the same, I guess, right? But since you're taking a maximum over fewer things, right? Then the maximum will decrease, right? The supremum will decrease. You're taking a supremum over a smaller set. Okay. So as you make these things finer and finer, right? Then the supremum is going to get lower and lower, right? Okay. Yeah. I'm sorry. Then the upper sums are going to get lower and lower. Okay. So that sort of motivates the following definition. We define the upper Riemann sum, the upper Riemann integral of f as, we denote it like this, and we define it to be the infimum of all the upper sums over all partitions. Okay. So you say, let's consider the upper sums over all partitions possible. Okay, right? All partitions possible, right? There's this crude, very crude, like you could take, this as your partition, right? In that case, your Riemann sum, your upper sum would be, just the area of this block, right? If you just took, the partition to be A, B, right? Then you would get this, right? But as you get finer and finer, the upper Riemann sums are going to get, are going to start dropping down closer and closer to the actual area. Right? Okay, right. So you take the infimum, you take the lowest, greatest lower bound over all upper sums, right? And as expected, you'd find the lower Riemann sum, the lower Riemann integral as this. Okay, and that finally gives us allows us to define what integrable means. We say f is Riemann integrable on AB if the upper sum and the lower sum are the same. Okay, so if the infimum of the upper sums equals the supremum of the lower sums, then we say it's Riemann integrable and denote that value by the integral. You can take it as an exercise or as a fact that if f is continuous on AB, then it turns out to be Riemann integrable. If that seems at least plausible, right? That if your function is continuous, then when you take the infimum of the upper sums, it agrees with the supremum of the lower sums. Let me give a non-example. Okay, and that is f of x being the characteristic function of the rational numbers. Okay, so that is, this guy is going to be 1 if x is rational, and 0 if x is irrational. Okay, so the function, right? Here's 0, 1. Let's consider this function on 0, 1. Say. Is this an integrable function on 0, 1? Well, at every rational point, right? So like at 0, at 1, at a half, right? At 1/3, at 2/3, at 1/4, 2/4, 3/4, at 1/5, 2/5, 3/5, 4/5, at 1/6, 2/6, etc. At every rational point, it takes the value 1, but at every irrational point, it takes the value 0. Okay. So you see that this thing is, it's sort of flipping back and forth, infinitely. In every interval you choose, there's rational and irrational points, right? And it's going to be jumping up and down. Okay. So if we think of, if we take some partition, right? Let's take a partition. Just arbitrarily choose a partition. What's going to be the upper sum over that partition?
1.
Yeah, 1, right? Because you're going to take the maximum value over each interval. Well, the maximum value is always going to be 1, right? And then you multiply by the width, So you're going to get 1 times the width of this guy plus 1 times the width of this guy, 1 times the width of this guy. But the sum of all those widths is going to be just the length of the base, right? And so you're going to get 1 times 1, right? So the upper sum, no matter what partition you choose, right? The upper sum is always going to be 1, right? For all, so observe, this is going to be 1 for all partitions, right? And so if we take the infimum of those guys, the upper Riemann integral is going to be 1, right? Because they're all equal to 1. So. Okay. On the other hand, what's the lower partition? Lower sum? 0, right? Because no matter what partition you take, the minimum value is going to be 0, right? Because you always have irrational points inside there, right? So this is going to be 0, and you see that the lower Riemann integral is 0, and those don't agree with each other. Okay, so this is a not Riemann integrable function. Okay. Those of you who go on and take a course where they teach you about Lebesgue integration, Graduate Real Analysis 1, 137, will be amused to hear that the Lebesgue integral of this is actually 0. And the reason is that the set of points where the function is 1 actually doesn't have much mass to it. It's a countable set, right? The rational numbers are countable, and any countable set is pretty sparse. In fact, any countable set is what we call a measure 0. And the irrational points, on the other hand, basically make up 100% of the mass here of this interval, right? So you say, well, look, it's 0 on 100% of basically 100% of the points here, and it's 1 on basically 0% of the points, and so the value should be 0. Okay. So this function is integrable, but not in the Riemann sense, but the Lebesgue sense. Okay. People are trying to get a sense of what integrable means, right? It just means that the infimum of the upper sums equals the supremum of the lower sums. Okay, so I should say that one of my uncles was a mathematician, and he's retired now. And he was a student of the mathematician Young, who's also famous in this area. And he repeatedly said that this is not the Lebesgue integral. It should properly be called the Young integral. That Young discovered it before Riemann, before Lebesgue. But I don't know the truth of that. Okay. Okay, some observations. I mean, most things in mathematics are actually misnamed. Like L'Hopital's rule is actually a result of one of the Bernoullis. The Cauchy-Schwarz inequality, the Russians call it the Cauchy-Schwarz-Bunyakovsky inequality, et cetera, et cetera. The Radon integral should probably be called the Funk integral, et cetera, et cetera. Okay. Or at least I've heard people say these, make complaints about all these things. Okay, some observations. First off, if your function is bounded between two values, so a simple observation, right? If your function is bounded between two values, then first off, the upper integral, I'm sorry, then for any partition P, the upper sum is going to be bigger than the lower sum. And the lower sum is going to be bigger than little m times the width of the base. And the upper sum is going to be smaller than big M times the width of the base. Okay, so I don't even know if you want to copy this down. This is pretty obvious, right? That the upper sum is going to be bigger than the lower sum, that the upper sum is smaller than the greatest value times the width of the base, right? The lower sum is bigger than the smallest value times the width of the base. It's just pretty obvious. Okay. Second observation requires me to define something first. So first definition is if you have P and P prime that are both partitions of an integral AB, and if P prime contains P, we call P prime a refinement. A refinement of P. Okay, it just means that, you know, you have one partition and then the other one has all those points and more, right? So it's just, you know, this partition contains the previous partition, right? So it has all of P's points and then some more points. Okay, then it's called a refinement. So observe, if P prime is a refinement of P, then what can you say about the relationship between the lower sums? This is actually what we said earlier. Right, you have a lower sum, and then you refine it. What happens to the lower sum? Is the refined one bigger, or is the refined lower sum smaller? Is the lower sum of the refinement bigger or smaller?
It'd be bigger or equal to?
Bigger than equal to, yep. Right, because you're taking the lowest value over a smaller set. Right. So if I throw this point in, now I'm taking the lowest value over a smaller set. So it will only get larger. Right. And similarly, what we said before, if we do that for the upper sum, the refined upper sum will only get smaller. This is what we said before. Yeah.
Wait, the refined set or the refined partition is the larger, is
That's
the one
right.
with more?
Yeah, with more points, yeah. Second definition, if P1 and P2 are partitions of AB, then we call the union P1 union P2 the common refinement of P1 and P2. Okay, so it's a refinement and it contains everything in P1 and everything in P2. Okay, so yeah, this is, I should say, this is not the most exciting stuff. If you're bored, then yeah, I think it's reasonable to be bored. We're basically just trying to get enough about the definitions so that we can talk about uniform convergence and Riemann integration. So we have just one more thing to do, and then we can actually get back to uniform convergence. Okay, so here it is. Theorem that that if you look at the lower Riemann integral, then it's always less than or equal to the upper Riemann integral. In other words, that the supremum of the lower sums is always less than or equal to the infimum of the upper sums. Okay, so we're gonna do a proof by contradiction. Suppose that the lower sum is strictly greater than the lower integral is strictly greater than the upper integral. Okay. So let's put a number line here, and we have the lower integral, and it's strictly greater than the upper integral. Okay. Now the lower guy is the supremum of the lower sums, right? The supremum of the lower sums. So that means that we can find lower sums that are arbitrarily close to it, right? It's the supremum of them. So we can, given any epsilon, we can find a lower sum inside here, right? And this guy is the infimum of the upper sums. So given any epsilon, we can find an upper sum that lies inside here, right? Okay. So what we're going to do is take our epsilon to be half the distance. Okay. Take our epsilon to be half the distance, right? But half the distance between these guys, and we say, well, okay, so we know that there's a lower sum inside here, and we know that there's an upper sum that lies inside here. Right. So there's some lower sum based on one partition that's bigger than the upper sum based on the other partition, right? Then there exists P1 and P2 such that the lower guy is strictly bigger than the upper guy. But now let P star be the refinement, the common refinement of it. Okay. Okay. So, right, then what can we say about the lower sum on P star? Okay. It gets bigger, right? We have it right there. We just have, yeah, right? It'll be larger than that one, right? And similarly, the upper sum will be less than this one. So, right? Upper sum on P star will be less than this. But that gives you a contradiction, right? Because what that says is that the upper sum on P star is strictly less than the lower sum on P star, right? Which is impossible, right? The lower, the upper sum on a partition is always greater than or equal to the lower sum on that partition, right? But we've got this contradiction here. Okay, so this was just sort of a crash course, and basically what I hope you get out of it are one, what the definition of Riemann integral is, right? What's a Riemann integral? And then just, I'd say, these basic facts, right? That, this fact here, this fact about the refinements, what happens when you refine it, and then this thing here. And these are all sort of like common sense, I'd say, right? So we're just putting this common sense on a firm footing. Okay. Okay. So yeah, so we just wanted to get a bunch of basic observations so that we can talk about uniform convergence. So now let's get back to the actual topic that we're interested in. So here it is. So okay. So suppose you have a sequence of Riemann integrable functions. We've got a sequence of Riemann integrable functions, and they converge uniformly to some function f. In that case, the f that they converge to is Riemann integrable. And two, the Riemann integral of f is the limit of the Riemann integrals of f sub n. Okay, so this is kind of what we hope for, showing that that uniform convergence preserves integrability. And the second thing is one of these commutation things, right? Because this f here is the limit of the f sub n's, right? So what this is saying is that the integral of the limit equals the limit of the integrals. Okay, that is, to find the integral of the limit function, you just take the integrals of each of these guys and then take the limit of them. Okay. So yeah, and remember that sort of thing is false for just pointwise convergence. Okay. Okay. So here's the proof. We say, okay, let epsilon denote epsilon sub n denote the greatest difference between f sub n and f. Okay, so this is what we called previously the sup norm metric, right? So this is the distance from this guy to that guy in the sup norm metric, right? And notice that e sub n goes to 0, right? Because the f sub n's converge to f uniformly. Okay, so that tells you that f is trapped between fn minus epsilon and fn plus epsilon. Right, here's your f, right? Here's your f sub n, right? Epsilon sub n is the biggest difference, right? Is the biggest difference between the two functions, right? And so if we take an epsilon n tube around f sub n, we see that f must lie in that tube. Normally, we usually think of the tube being around f, but this time we're going to think about the tube being around f sub n. In any case, it's still true. Okay, so now we're going to take we're going to take lower and upper Riemann sums of things. So we'll say, well, look, if we take the lower Riemann sum, we have this inequality here, right? So that tells us that the lower, if we take the lower Riemann integrals, then this equality still holds. Because we have this pointwise inequality, and it's still going to hold true when we take lower sums. Okay, and then we do something on the right side for upper sums, right? That this guy is controlled by the upper integral. Okay. Okay, and by the theorem that we just proved, we know that this thing is always less than or equal to that thing, right? That the lower integral is always less than or equal to the upper integral. Right? So by the theorem. Okay. Okay, everybody all right? Yeah, nothing going on here. So now remember the f sub n's are Riemann integrable, right? So when we take the lower integral of this, we just get this is going to be just this. Right? And over here we're going to get the integral of f sub n plus plus epsilon n. Right? Because for f sub n, the lower integral and the upper integral are the same thing. And certainly, for a constant, constants are definitely Riemann integrable. So, yeah, we can do that. Yeah. Okay. Okay. So now we observe that, look, if we take this guy minus this guy, right? We take the bigger guy minus the smaller guy, right? That's bigger than 0, certainly. But it's also smaller than this guy minus this guy, right? Right. If I've got 4 numbers, A, B, C, and D, and they're increasing, the distance, this minus this is smaller than this minus this, right? That's all I'm saying here, right? So we take the difference of the 2 interior guys, we take the difference of the exterior guys. But the difference of the exterior guys is just 2 epsilon, right? Because we get f sub n minus f sub n, right? And so what we get here is epsilon times b minus a. Okay. And then, if you let n go to infinity, you get that these things are equal to each other, right? Because they're trapped between 0 and 0. The difference is trapped between 0 and 0. Get that this thing actually equals this thing, which is the value. Yes, Sam?
Will you explain again how you got the 2 epsilon n?
Yeah, because this minus this is smaller than this minus this, right? So that second thing is this minus this, right?
Oh.
There's a plus here, there's a minus here, so we're going to get, as my son says, the minus combines with the minus and makes a plus. Yes?
Just wondering, where did the 2 go from
Oh,
the?
sure.
Oh, okay.
It doesn't matter.
Yeah.
Yeah. As n goes to infinity, it still goes to 0. Yeah, but you're right. Absolutely. Okay. Right. Okay, so that gives it to you, right? What do you get? F is Riemann integrable. Right? F is Riemann integrable, and you see that kind of by the same reasoning, right? The Riemann integral is trapped between this and this, right? Further, going back there, back here, we see that the Riemann integral is trapped between fn plus epsilon n and the Riemann integral of fn minus epsilon n. Right. And so when we take the limit, we see that this thing equals the limit of the integrals. Right. Again, let n go to infinity, and we get that the limit. Sorry, let me write it over here. Let n go to infinity, we get that the limit of this is less than or equal to the Riemann integral of f, which is less than or equal to the limit of that, right? Which is the same thing, right? And so this. So the integral of the limit is the limit of the integrals, as we hoped. Okay. Let me just make one. I think I have enough time to make the corollary. right? If you have a bunch of Riemann integrable functions, sorry, this is the notation, the Riemann integrable functions on AB. If their sum converges to f uniformly, then what do we see? We see that just by the theorem, the integral of f equals the limit of the integrals of the partial sums of that infinite series. Right? The integral of the limit is going to be the limit of these guys. Actually, maybe, no, I'm gonna leave it that way. Okay, but these integrals of the partial sums, this is just a finite sum, so we can pull the sum out, right? So this is the limit as n goes to infinity of the sums of the integrals of the functions. Okay, so this part, I should sort of leave out. This isn't part of the theorem. The point of the theorem is this, that the integral of the limit is the limit of the sums of the integrals. Right? So, so for example, if f of x equals some power series, suppose f of x is some power series, and let's say that the power series converges uniformly to f. Okay, what this theorem says is that then the integral of f on some interval is going to be the limit of the integrals of each of those monomials. Okay. In other words, you can integrate the terms term by term. Okay. One can integrate term by term. Right? So basically what this is saying is that if you're taking the integral of some uniformly convergent power series, then it's okay to just take the integral of these terms. It's okay to take the integral, term by term. Okay, that's something that will be very handy in complex analysis next term. Because what you'll see is that power series always converge uniformly within a smaller disk than their radius of convergence. If you take complex analysis, there'll be a radius of convergence, and turns out that in any smaller disk, you're guaranteed uniform convergence, and so you can do term by term integration. Okay, sorry to keep you over. That's it for today. Next time we'll do differentiation, uniform convergence and differentiation. And then we'll probably go right into something called equicontinuity, and hopefully try to get to the big result called the theorem of Ascoli-Arzela. That's the climax of the course.